This lesson is going to cover section 4.8. Antiderivatives. All right, section 4.8 is on antiderivatives. Now, we're going to start with a definition. This is our linking section between chapter 4, applications of the derivative, and chapter 5, our introduction to the integral. So section 4.8 is our segue section. It moves us from chapter 4, the derivative and what can the derivative do for me, into chapter 5 and what is an integral, the other big idea that we cover in this course on. Because remember, we stop, right? Our course stops at section 5.5. Section 5.5 is use substitutions, and that's where we stop. So we're going to begin section 4.8 with a definition. And this is the definition of an antiderivative. It says a function f. And our notation here is going to be capital F. A function capital F is called the antiderivative. Is called the antiderivative. Yeah, that was funny. Of little f on an interval I. If. And this is the important part, right? This is the part that matters. If the derivative of capital F equals f of x for all I, for all x in I. So we're changing up the way we think. We're going the other way here. The antiderivative, right? The antiderivative is the person, the function in this case, whose derivative equals our original function. We're not taking the derivative of our function f. We're not doing that, right? That's not the game. The game is not take the derivative of f. We've done that for 2 chapters. We know how to do that. The question we're being asked here is, whose derivative equals f of x? That's the question, right? And so let's write that down. The question is, whose derivative equals f of x? So what do I mean by that? Well, let's just, before we move any further, let's just take a look at an example, right? If I write down f of x equals x squared, and I ask you to find the antiderivative, of f of x. What are we being asked to do here? What we're being asked to do is to find the function capital F of x. That's our symbol for the antiderivative in section 4.8. That'll change when we get to chapter 5. But in chapter 4, section 8, we're asked to find the function f of x such that, right, so we want to find f of x such that the derivative of f of x, capital F of x, is our f of x. So whose derivative equals x squared? That's what we're being asked to do. Now this for us, this is a change in direction. we're not used to going backwards. And that's literally what we're doing here. We've been given a function, and we are asking ourselves, somewhere there is a function whose derivative equaled x squared, and we're supposed to find that function. So we're not taking the derivative of this. We all know the derivative of this is 2x. That's not what we're looking for here. We're looking for the function whose derivative is x squared. And it's going to take a few problems, a few examples, a bit of time for us to get our brain trained to go in that direction. It's a very normal experience. So how does one go about this? Well, we analyze and synthesize. We look at what we're given and we ask ourselves, all right, somebody out there has a derivative that equals x squared. And I want to know who that is. Now, many of you have probably already come to the conclusion that if I start with x cubed and I take the derivative of that, right? I take the derivative of x cubed, I'm going to get 3x squared. And that's a great start, because if you look, we have the x squared that we're looking for. We want the function, whose derivative is just x squared. And right now, we have a candidate. We proposed x cubed. We took the derivative, and instead of getting x squared, we got 3x squared. And so what do? Well, we're going to make an adjustment. We're going to adjust this. We're going to ask ourselves, what could I do to that to, in essence, make this 3 disappear? If I could get that 3 to disappear, I would have the function whose derivative is x squared. And so the adjustment, it's not rocket science, and many of you have probably already thought about it right now. The adjustment is, I can't avoid this 3. This 3 is going to be here. When I take the derivative of this by the power rule, the 3 is going to come down. What am I going to do? I can't cross it out. But what I could do, perhaps, is I could put a coefficient out in front of the x cubed in such a way that that coefficient, not arbitrarily chosen, of course, chosen logically and with reason, so that when we do take the derivative, the constant, right, the derivative of the constant times the function, the constant stays out in front, we take the derivative of x cubed, that gives us 3x squared. And now, 3 times 1/3 is 1, and we get the function whose derivative is x squared. Our antiderivative, right, that's what we call this, we would say capital F of x equals 1/3 x cubed, or we could write that as x cubed over 3. This is the function whose derivative is f of x equals x squared. So this is the journey that we are now undertaking. We're going backwards. We're reversing our approach. Instead of looking at it from what's the derivative, we've had chapter and a half working with that. Instead, now we are changing our perspective. We're saying, who is the function that gives me this as a derivative? All right? Now, I'm gonna ask a simple question. That is this the only function whose derivative turns out to be x squared? And if you think about that for a second, right? If you ponder that question, you're going to realize the answer to that is no. It's no. Because what about the derivative of this function? F of x equals, we'll go ahead and write it as x cubed over 3. What happens if I have a 7? Well, if I have a plus 7, the derivative of this, right, the derivative of this is going to be 3x squared over 7 is 0, and I'm going to get my x squared. Now, there's nothing magical about the 7, right? I could have picked, as it turns out, I could have picked any constant to place there. Because if I were to take the derivative of this, right, we'll go ahead and write all the steps out. The derivative of this, f prime of x, that's going to be the derivative of x cubed over 3 plus the derivative of our constant. And what is that going to equal? That's going to equal 3x squared over 3 plus 0, the derivative of constant 0, and that's going to give us x squared. So, if we have any constant, when we take the derivative of that constant, we get 0. So when we're taking antiderivatives, it is not the case that only one function turns out to be our answer. It's the case that all functions plus a constant turn out to be our solution. So, let's add that definition to our notes. So, we present this as a theorem. If f is an antiderivative of some function f on interval I, then the most general antiderivative of f on I is f of x plus c, where c is an arbitrary constant. So, what does this mean for us? It means when someone asks us to find the antiderivative of a function, we want to make sure that we provide the full answer to the question, right? The full answer to the question. Because if we don't, right, well, let's just do a problem and see what would happen then, right? Let's say f of x equals sine x, and they want us to find the antiderivative. Let's find the antiderivative. Well, what does that mean? That means we want to find the function whose derivative is sine. We have a good guess, right? We have a good guess. We think whose derivative equals sine? F of x equals, and we know cosine, right? We know cosine has something. There's a relationship between cosine and sine when it comes to derivatives, and we think to ourselves, okay, I'm going to start with cosine. Usually we have an idea of where to start with these antiderivative problems. So I'm gonna think to myself, all right, I'm gonna begin with f of x equals cosine x, and that's a great place to start. So what do? Well, we check our work. We think, what is the derivative of cosine? Well, the derivative of cosine is not sine, right? That's not the derivative of cosine. The derivative of cosine is negative sine. So how could one fix that? What would we do? Well, if we put a negative sign out in front, right? We put a negative sign out in front, what would happen if we took the derivative of negative cosine? Well, the derivative of negative cosine, that's a constant, so that's going to stay. So the derivative of negative cosine, right, if we just wrote that out, what does the derivative of negative cosine x look like? Well, the minus stays because it's a constant times a function, so that stays out in front. We take a derivative, and then we take the derivative of cosine. The derivative of cosine, of course, is negative sine. Two negatives make a positive. We write down sine x. And if we're taking an exam or a quiz, we feel very, very fulfilled, right? We're like, hey, I got that problem right. Almost. We almost got that problem right. You found, for the answer to the problem, you found that the antiderivative of sine is negative cosine. But that's not really what you found. What you found was the antiderivative of sine is negative cosine x plus 0. Now that indeed is one answer to the problem, right? That is an answer. That is a solution to the problem. But when we ask you to find the antiderivative, we don't mean to find the antiderivative in the sense of finding us only one antiderivative. What we mean is for you to find us the antiderivative in terms of all of the antiderivatives. See, there are an infinite number of solutions to this problem because the real solution to the problem is f of x equals negative cosine x plus 0. No. The real solution is f of x equals negative cosine of x plus c, where c is an element of the reals. Now, why is this a big deal? Well, it's a big deal because out of all the answers to this problem, you found one, right? Your solution is one answer. There are an infinite number of possible correct solutions to this problem. You proposed negative cosine of x plus 0 as a solution. It indeed is. But my question to you as an instructor then is, what about negative cosine of x plus pi, or negative cosine of x plus 13, or negative cosine of x minus 6? You've left out quite a few answers. The only choice I have, of course, is to give you the partial credit that you've earned. You found one answer out of an infinite number of answers, and we all know 1 divided by infinity is equal to 0. And then when you get your midterm back, or your quiz back from me, you're less than satisfied with the number of points that you've earned in my partial credit methodology. But we should both be comfortable with what happened here. You provided one answer out of an infinite number of correct answers, so I provided you with the correct number of points. So let's make sure that when we find our antiderivatives, we do not forget our arbitrary constant c. Right? You want to remember that because there are an infinite number, right? There are an infinite number of correct solutions to this question. So how does one go about finding antiderivatives? Well, the good news, and it is going to be the good news as we move into chapter 5 and start talking about the integral, antiderivatives are what we've written. Right? They're the function whose derivative is f. So we're looking at the derivative and we're going essentially backwards to find the antiderivative. What's the adjustment that we're going to have to make? Well, first we're going to have to adjust the way we think. We're going to have to think reverse instead of forward. The other big adjustment for us to make is if someone writes down a function for us, we can generally find the derivative of that function. If someone writes a function down, if we just arbitrarily open our calculus book and they write a function down, finding the derivative of that function is very straightforward. We have some very formal rules, we have some very formal techniques, we have product rule, quotient rule, chain rule. We can find the derivative. Antiderivatives don't work like that. In fact, finding the antiderivative of just any function is virtually impossible for you and I to do just by following a set of steps. There are tables and tables and tables of antiderivatives because contrary to finding the derivative, finding the antiderivative, well, I like to say any calculus student can find a derivative, but it takes a talented calculus student to find an antiderivative. Not judging anybody out there, just pointing out that the antiderivative, finding the antiderivative is more of an artistic approach to calculus. Finding the derivative is, it's trying to smash a marshmallow with a hammer. Anybody can do it. So, where do we begin our journey in the antiderivative world? Well, there are a few rules, a few firm rules that we need to write down. And they generally are presented to us in the form of a table in our textbook. And that's how it works in our section 4.8. In section 4.8, we are given a table, and they say, hey, here are some antiderivatives that perhaps if you want to be successful as a calculus student moving forward, you may want to know these antiderivatives. Now, many of you moving through pre-calc were presented with this similar kind of an approach to your trig identities. We said, hey, if you want to be successful in calculus, knowing your double angle and your half angle identities are important. You should commit these to memory. None of us want to take a lie detector test on whether we have all of our trig identities committed to memory. So let me just put this out there as a word of caution. Don't treat your antiderivative formulas as perhaps you may have treated your trig identity formulas. So I'm going to go through this table, just kind of summarize each one of these, talk about them a little bit, and see if each of us are comfortable. Then I'll do a few examples, and that's all there is to antiderivatives. Now, if we do not have this table of antiderivatives memorized, we're really, really handicapping ourselves as we move forward. So I suggest to my students, note cards. Anybody can read the front of the note card to you and the back of the note card. They don't have to know what an antiderivative is. They can just look at the front, read it to you, and then, if they say cos x, well, they mean cosine x. And if they say sin x, they mean sine x. And we can practice with our note cards. So, what are the general rules we need about antiderivatives? And in Calc 1, this is pretty much the end all, and I don't know, have any idea how that expression is. But anyway, it's the end of where we're going to go when it comes to finding antiderivatives. In Calc 2, we'll teach you some additional techniques, but in Calc 1, this table is going to be our number one source for finding antiderivatives, and for later in Chapter 5, finding integrals. So, how is this table set up in our book? Well, in our book, it says function, then it says particular antiderivative. Then it says, so this, now what do we mean by particular? We mean no constant. No constant. That's what we mean. The phrase we use for that is a particular antiderivative. If it had a constant, we would call it the general antiderivative. So what are the functions that they expect us to be able to find the antiderivatives of? Well, first, they say, what happens if you have a constant times a function? If you have a constant times a function, then your antiderivative is going to be that same constant times f of x. And we'll do examples of all of these as we move through some examples here in a second. So let's just get our table written down in our notes so we can have it to refer back to, and then we'll move through some examples where we have an opportunity to take a look at each one of these, perhaps in practice. Now, what happens if I'm presented with a function plus another function. And they want me to find the antiderivative. Maybe this is sine x plus secant squared x, and they want me to find the antiderivative of that. Well, the nice thing is the antiderivative of the sum of two functions is the antiderivative of the first function plus the antiderivative of the second function. Now, what about x to a power? Right? You and I have already looked at this. We did an example. This is our introductory can we see the process example that we talked about in the beginning. We used x squared. If you remember, we ended up with x cubed, right? X cubed, you go back and look at your notes, we ended up with x cubed over 3. So the idea here is the antiderivative, if this is a 2, I want this to be a 3. I'm going to write a 3. I want that to be a 3. So if it's a 2, I want it to be a 3, I add 1. Then I divide it by 3, so I will divide by n plus 1. Now, if we just, in our heads, take the derivative of this, this is a constant, this is not the quotient rule, this is a constant. So the derivative of this, the n plus 1 is going to come down in front, that's going to cancel the n plus 1 on the bottom. We're going to subtract 1, n plus 1 minus 1, x to the n. Now, if we take a quick look at this formula, right, if we take a quick look at this formula, we see a glaring problem with this formula. Over here, if n equaled negative 1, we would have negative 1 plus 1 on the bottom. That would be 0 and undefined. So one of the things about this, we call this the power rule. One of the things about this rule we have to keep in mind is n cannot be negative 1. It cannot be negative 1. Now don't panic. It's not like we're going to leave you hanging very long on that, because the very next rule is, what is the antiderivative? Because 1 over x is indeed x to the negative 1, isn't it? So what is the antiderivative of that? The antiderivative of that is the natural log of the absolute value of x. If we take the derivative of the natural log, we get 1 over x, right? That's how antiderivatives work. Remember, antiderivatives work where the derivative of the antiderivative has to equal our function itself, right? What about e to the x? Whose derivative equals e to the x? Well, that's one of our favorite answers of all time, right? Because the derivative that equals e to the x, well, it is e to the x. The derivative of e to the x is e to the x. So e to the x, not only is its own derivative, it's also its own antiderivative. Now, of course, remember, we're doing particular antiderivatives. If we were doing a general antiderivative, the general antiderivative of e to the x would be e to the x plus c. Right? E to the x plus c. What about cosine? Now, we rarely start with cosine, right? We normally start with sine. Why do we start with cosine? Well, because cosine's the easier of the two. What do I take the derivative of to get cosine? To take the derivative of, I take the derivative of sine. The derivative of sine is cosine. Okay. Sine, we've already looked at this one. You and I looked at this one previously. What is the antiderivative of sine? Well, the antiderivative of sine is negative cosine. We have to remember that when we take the derivative of cosine, we get negative sine. So to fix that, I have to put a minus sign out in front. What about secant squared x? Who do you take the derivative of to get secant squared x? Right? Somebody's derivative is secant squared, and that is tangent. Secant x, tangent x. Whose derivative is secant x, tangent x? We know the derivative of secant is equal to secant x tangent x. Therefore, secant x is the antiderivative of secant tangent. Right? Again, we're going backwards. It's going to take a while for you to get used to that. From here, we get a couple more. We get 1 over the square root of 1 minus x squared, right? whose derivative is 1 over the square root of 1 minus x squared. Well, that's inverse sine. I think I can squeak one more down here. It's the last one. It's 1 over 1 plus x squared. Right? Whose derivative is 1 over 1 plus x squared? That is inverse. Now you'll notice in this table that we've constructed right here, and I'm going to leave this on the whiteboard. I'll work my examples out over here so we can have this to refer back to. But you'll notice that we did not, right, we did not put cosecant squared, and we did not put cosecant x, cotangent x here. And that's because your authors believe that, you know, if you can keep track that the antiderivative of secant squared is tangent, then you can probably keep track of the antiderivative of cosecant squared, right? Whose derivative is cosecant squared? Well, the derivative of cotangent, right, cotangent, the derivative of cotangent is negative cosecant squared. So we would say then that the antiderivative of cosecant squared would be minus cotangent, all right? And they assume that you can keep those things straight, and so they do not reiterate those in this table because they figure you can follow along. All right, where do we go from here? Well, we're going to do some examples. I mean, that's what we're left with. We're left with working out some examples. When we get done with the examples, then you're free and able and capable to go out and attack your homework problems. So let's just grab some examples, right? See what we can do here. So if we start, right, if we start with a function, and this is one of the things I find interesting about our book, is they tell us the antiderivative is the capital letter, and then in the first example, I'm going to write it like this, right? They give us g of x equals 4 sine x. Now this is example 1. This is example 1 we did previously, right? Example 1 was our x squared. This is the very next example, plus 2x to the fifth minus the square root of x, all divided by x. So when you look at this example and you think to yourself, okay, this is example 2, and already this function is much more complex than anything we have over here in our table, hopefully that gives you some level of comfort. You look at that and you think to yourself, all right, maybe this isn't as bad as I think it's going to be, because already we're into formulas that are way more complicated than the formulas that are over here. This problem, right, this problem has this term. Now this is a moment for us to pause, take a look at this, and to write something in our notes, right? We want to write something in our notes about this example. And that is this: I will not be fooled by a common denominator question. All right, this is a declaration. Why do we write this down? Well, because when it comes to antiderivatives, instructors, we love to put common denominator problems down. There's no quotient rule over here. There's nothing over here that addresses a quotient. And so we present this as a problem because we're mean. I guess that's why we present it as a problem. No, we're trying to make sure that you're thinking your way through the problem. How does one go about solving this? How does one find the antiderivative of a problem such as this? Well, the first thing we're going to have to do, right? And notice I'm still working with capital G of x. I haven't found the antiderivative yet. I'm going to rewrite this problem, and I'm going to rewrite it like this. This is what we mean when we write, I will not be fooled by a common denominator question. There is not a rule over here on our list of antiderivatives to deal So what are we expected to do? We're expected to turn it into a problem that doesn't have a common denominator. That's what we're expected to do. That's our first solution strategy. These are very, very common questions, pardon the pun with common denominator, but common questions on an exam, and we don't want to be fooled by this. This is something that we can walk into an exam or walk into a quiz capable and willing and ready to solve by remembering that we can break up a common denominator into multiple fractions. We are conditioned throughout math to take things that have a common denominator and combine them, right? That's what we're conditioned to do. Here, we have to go against that conditioning. We have to split it apart. Now, if we rewrite this, right? If we rewrite it, again, we're working with capital G. I'm not doing any work here. In terms of the antiderivative, I have 4 sine x plus, this is 2x to the 4th. This is x to the 1/2. So this is minus x to the minus 1/2. Right, when we simplify this. Now we have something that we can take the antiderivative of. The antiderivative of this, little g, right, whose function is the derivative. The antiderivative of this, we have a constant, 4 times sine. We have a rule that right here that says if you have a constant, you just keep the constant. So we write 4. We need the antiderivative of sine. The antiderivative of sine, if we check our table, the antiderivative of sine is negative cosine. So that's going to be 4. We're going to go ahead and write negative cosine x right there. We'll clean it all up on the next line. Let's don't try to do too many things at once. We're just learning this. Plus, we have a 2. Right? We have a 2. Now, that's the same rule, constant times function. We're going to put the 2 out in front. How do we take the antiderivative of x to the 4th? Well, that's our power rule, and our power rule says we add 1 and divide by the new exponent, right? We add 1, divide by the new exponent. So this is going to be x to the 5th divided by 5. All right, we just find the new exponent and divide. Minus, and what do we do over here? Nothing here says n can't be negative. It says n can't be specifically negative 1. It can be any other value. N can be any real number other than negative 1. And of course, if it's 0, it would not be, we would have a constant here. So how am I going to address this? I'm going to do exactly the same thing I did before. I'm going to add 1 here. Right? And what do we get? What do we get when we add 1? Well, negative 1/2 plus 1 is going to be x to the positive 1/2, right? Now, why is this example here? Well, this example is here because it covers so many things that we need to be aware of. First, it covered the common denominator question. Now, it's going to allow us right here. Okay, one thing we can do, right? We find the new exponent, we divide by it. We could all do this. Many of us are not very good at dividing by fractions. I don't know if I'm allowed to say that. Maybe you're fabulous at that. Maybe some of you are more honest with yourselves, and you're going to admit to the fact that when you divide by fractions, things get a little less comfortable. So here's how we approach this, right? I have a half right here. I'm not going to divide by a half. I'm going to multiply instead by the reciprocal of this. It saves me, right? It saves me from having to divide by a half. Because what happens? If you take a and you divide by a fraction, right? What do we know? What we know is that's really a times the reciprocal. That's what we were taught back in elementary school about dividing by fractions. So since we know that a number divided by a fraction is that number times the reciprocal of the fraction, why don't we just use that as our problem-solving methodology over here and avoid the whole dividing by fractions, which we may or may not be good at. So what do we end up with here, right? Now, you'll notice I forgot, so thank you for pointing it out. I appreciate that. We'll put our C on there. So what do we get here? We get minus 4 cosine x plus 2/5 x to the 5th minus 2x to the 1/2, right? Plus this is our antiderivative, right? This is our solution. This is our answer. This is our answer to the problem. This is the function whose derivative is g of x. Now, one of the most frustrating things about teaching this in a Calc 1 class is we give you an exam, we give you a quiz, you do this work, it's beautiful, you're very confident in your answer, and I respect that. I respect the fact that you have confidence. However, the check for this is relatively simple. You just spent 2 chapters learning how to take a derivative. The check for this, right, not that anyone does the check, but the check for this is to just find g prime of x, which is supposed to be equal to g of x. That's literally our definition of the antiderivative. Many of us, when we teach this, we often wonder to ourselves, or maybe we wonder out loud to you when we're handing back the midterm of your quizzes, why didn't you check your answer? It would have taken not very long, and it would have perhaps allowed you to discover a mistake that you might have made that you could have then gone back and fixed and gained full credit on the question. So how does one, what do you mean how does one? One just takes the derivative. We all know the derivative of cosine is negative sine. Negative times negative is going to be positive, so that's going to be 4 sine x. The derivative here is going to be 2 times 5, right? That's going to be 10 divided by 5. We subtract 1, that's going to be x to the 4th. The derivative here is going to be minus 2. Down comes the half, so we get times a half. We take away 1, we get x to the minus 1 half. And if we clean this up, we have 4 sine x plus 2 x to the 4th minus x to the minus 1 half, which is right here. That's not asking a lot. That's worth perhaps 5 or 6 points on your next midterm, and your justification for not doing it is exactly. So, that's an example of a problem that we can encounter in our homework, where it says, find the general, right? The general. Oh, now I didn't take the derivative of c because I was being condescending down here, and I apologize for that. But I know you know the derivative of c is 0. My students accept that condescending attitude, and they know that it's presented with admiration. So, if you're not in my class, well, welcome to meeting Kevin Rayner. So I'm going to erase this, and let's do another example, right? One more, and then you'll be ready for the homework on this section. So what else could they ask me to do, right? What is another potential problem that they could ask me to work out? Well, it is possible that they could ask you to find a solution for a specific value of c. And let's write down a problem and see what we would encounter for a question like that, right? So we would have something like now sometimes instead of writing capital F, they write F prime, and then they ask us to find F, right? F would be the antiderivative of F prime. So F prime equals e to the x plus 20 times 1 plus x squared to the negative 1. Now, if that was the entire problem, then this would be a question where they want us to find a general solution, right? There's no other information. We would take the antiderivative of this. We would find the function f. We would then check, right, because we want to make Kevin happy. We would check, and then, or at least we'd tell him we're going to check. It's not like I'm not going to know. And then, what else could they possibly provide us? How could this question be different, in other words, from the question we just encountered? Well, this question comes with this added little piece of information. It says, by the way, when you plug in 0, you're going to get 2. And what does that mean? Well, if we go back and take a look, just look back on your notes. I mean, I can't see it on my notes because being the genius I am, I erased it. But if you go back and take a look at your answer, right, the answer we came up with for our problem, if you take a look at that problem, that solution, We have a plus c off to the side there. Now that c could be 1, that c could be 0, that c could be 3. In fact, that c is any real number, which means if you asked your graphing calculator to graph our solution, we would get our solution plus 0, let's say. Then you could say plus 1, and then plus 2, and plus 3, and plus 4, and plus 5, and plus 6, and plus 7. And I'm moving my hands up the whiteboard because when you add a constant to a function, we all know that shifts that function up that many spaces. You could say minus, and you could move that function down. Minus 1, minus 2, minus 3, minus 4. So the solution to our problem is an infinite number of curves. Every one of those curves is represented by a different choice for your value of c. As you changed your value of c and asked your calculator to graph it, it would draw literally the same graph, and it would move it up or it would move it down based on your choice of c. Well, what does this problem say? This problem says, out of all of those graphs that can shift up and shift down, right? The one I want you to provide me, the answer I want you to provide me this time is I want you to provide me the answer that goes through the point 0, 2. I want one particular solution here. That's what we say. We say this is a particular solution. I want the solution that goes through the point x is 0, y is 2. That's the solution I want. I don't want all the other graphs. I want the graph that goes through that point. So when we find the antiderivative of this function, we are going to be responsible for finding only one solution, not the infinite number of solutions, but just one, and we want to find the solution that goes through the point 0, 2. Right? Now that sounds like it's going to be a little bit more work, and I'm going to be honest, a little bit more work was, those words were, well, they were chosen carefully. It is just a little bit more work. It's not a lot more work to do that. So where do we begin? We begin working this problem out just like we worked out the previous problems. Right? We're going to find the general solution to this problem. So how are we going to go about doing it? Well, if we rewrite this, right, because right now this doesn't look like anything over here. If we rewrite this, we get e to the x. Now we all know the antiderivative of e to the x is e to the x. Right? I mean, we were thrilled to see that presented in our problem. This is 20 divided by 1 plus x squared, right? 1 plus x squared to the negative 1 is 1 over 1 plus x squared. That is also an antiderivative that we are comfortable with, right? We know that's inverse tangent. So finding the antiderivative here is going to be a lot easier, a lot less steps, a lot less thinking, actually, than finding the antiderivative in the previous problem. So what is our antiderivative here? Well, it's going to be f of x, right? The antiderivative of f prime is f. We take the antiderivative of e to the x, that is e to the x. Now this is a constant, right? This is a constant. This is really 20 times, right? This term right here. This term right here is really 20 times 1 over 1 plus x squared, isn't it? That's really what that is. So that's a constant. Constant times a function will be the constant out in front. We want the antiderivative of this, and we know the antiderivative of that is inverse tangent. Plus c. So that is our general solution. That's the solution that represents what we call a family of solutions. A family of solutions. The family has a lot of different members. Right? We could have c is 1, c is 2, c is 3, c is 4, c is negative 1, c is negative 2, c is negative 3. Of course, it could be fractions, it could be decimals, it could be irrational numbers. C can be any number we want. So we call that a family of solutions. That's what we call it. Not to scare anybody, but this is an equation with a derivative in it. This is a whole world of mathematics out there called differential equations. And all you engineers in the class and all you math majors in the class, you're going to get to explore the world of differential equations. Differential equations are equations with derivatives in it. We learn how to solve equations with derivatives in it. Did you really think we're going to teach you derivatives and then not put them in equations? I mean, come on. We put square roots in equations after we taught you square roots. We put trig functions in equations after we taught you. We put rational functions in equations after we taught you. This is what we do, right? We teach you somebody, we shove it in equations. It's the name of the game. So we're actually solving differential equations here. But we're not calling it that, right? We're calling it antiderivatives. All right. So back to our problem. Our problem right now, this, right? This is our general solution. That's what this is. That's our general solution. Now we want a particular solution. We want the solution that goes through the point x is 0, y is 2. Now how are we going to find that? Well, we know it's x is 0, y is 2. We're going to plug it in. After all, this is f of x. So we know f of x is 2. And we know x is 0. Well, if we take a look at this, right, we're going to solve for c. That's the answer, right? The answer to how do I change a general solution to an antiderivative problem into a particular solution is you find the requested value of c. So we solve this equation. This is 2, right? This is 2. E to the 0 is 1. Inverse tangent of 0 is 0, so that's plus 20 times 0 plus c. Move the 1 over here, and we get 1 equals c. So our solution, right? Our solution is c equals. I'm taking a look at this for a second. I just don't feel good about this. Why do I not feel good about this? Oh, it's perfect. All right. So c is equal to 1. So what does our particular solution look like? What is our particular solution? Our particular solution is f of x equals e to the x plus 20 inverse tangent of x plus 1. That is the solution to this differential equation, or that is the antiderivative that goes through the point x is 0. So these are the types of problems you're going to encounter in the homework. Now, the only extension to this, right, the only extension, I wasn't going to do this example. I mean, we're pushing 53 minutes on this video, but I feel like I don't want to leave you hanging. It's not like, you have anything else to do right now. And after all, you're the one that chose to watch this. So if I erase this, right, I'll do one more. Example. Because there is, it's not a new kind of problem. It's really not. It's not a different kind of problem either. It's the same kind of problem we've worked on already. But there is the possibility. Right? There is the possibility that you could get problems that look like this. F double prime of t equals 2e to the t plus 3 sine t. Now you'll notice this is different than the 2 examples I've given you before, because this starts with the second derivative, right? For all you physics kids, this starts with acceleration. The first derivative is going to be velocity, and the next derivative is going to be position, right? So, where do we go from here? Well, let's just take a look at this, right? Let's take a look at this and see where does this go? Well, the problem that I'm looking at in the book that I'm taking this problem from, this problem has 2 initial conditions. It says, by the way, we want the particular solution that goes through the point 0, 0, and we want, in addition to that, we want it to go through the point pi 0. Now, why do we have two what we call initial conditions, right? That's what we refer to these as. We refer to these as initial conditions. Why do I have two initial conditions? Well, I have two initial conditions because I've got two derivatives, right? I've got the second derivative of f. So when I take the antiderivative of f double prime, I'm going to get a constant. Then when I take the antiderivative of f prime, I'm going to get a second constant. So I'm going to need two initial conditions before I can eliminate, right? Before I can eliminate those two constants. So how do we attack this problem? Exactly like we've attacked the previous problems. We do nothing different. We do exactly the same steps. But now, when I find the first antiderivative, that's going to be f prime of x. When I take the antiderivative of f double prime, I get f prime of x. So when I take the antiderivative of this is a constant, so that stays. The antiderivative of e to the t, of course, is e to the t, plus, I got a constant, 3. Now the antiderivative of sine, remember the antiderivative of sine is negative cosine. So I'm going to write that here, and I'm going to go back and I'm going to make this a minus sign. Okay. And I'm going to add my constant. Now, if one of these initial conditions had a prime on it, which they do not in this example, I picked this example specifically because they don't, but if one of these initial conditions had a prime, then I would use that initial condition right now on f prime, and I would solve for c. But in this case, our initial conditions are both in terms of f. So we must now take the antiderivative of this. The antiderivative of 2e to the t, well, it's 2, and the antiderivative of e to the t is e to the t. Now here we have minus 3, right? We have a minus 3. The antiderivative of cosine is just positive sine, so that's a positive there, and that doesn't change that sign. Now here we have to think about this for a second, right? We haven't seen that anywhere over here. I haven't even addressed it, which is kind of one of the reasons I thought I needed to do another example. What is the antiderivative of a constant? Well, the antiderivative of a constant is c times x. Because why? Well, because the derivative of cx is c, and that's what an antiderivative is. One way to think about it, I'm not saying this is a good way to think about it, but one way to think about it is to think that there's an x to the 0 right there. And if there is indeed an x to the 0 right there, well, what do? We add 1 and divide. We add 1 to 0, that gives us x to the first. We divide by 1, c times that. Now, we did take an antiderivative, so we need to put another constant down. I like to use d. Some books use c sub 1 and c sub 2. I get confused with c sub 1 and c sub 2, so I like to use d. Now, I have f of x. I have two constants. I have two initial conditions. My Algebra 1 teacher, bless her soul, told me that, if you have two equations and two unknowns, you can solve that. And that, typically on an exam or a quiz kind of question, is where a problem like this leads. Now this problem is a little nicer than that. It doesn't lead to a two equation and two unknown situation, but we're going to talk about this as if it were a two equation and two unknown situation to get you ready for an exam level question. So what do? We plug this in. I'm going to plug in f of 0. F of 0 says, when I plug in x is 0, remember this is your x, this is your y over here. I'm supposed to get 0, right? That's my y value. This is 2e to the 0 minus 3 sine of 0 plus c times 0, x is 0, plus b. Now this term right here, c times 0, that's 0. Now that doesn't always happen. And if that doesn't turn out to be 0, then we would end up with an equation with two unknowns in it right here. Perhaps this would be, say, 2c plus d. So we would get an equation with two unknowns. Don't panic about that. When you plug in this, you're going to get a second equation with two unknowns. And then you're going to make your Algebra 1 teacher proud, and you're going to solve the system of equations and you're going to find a value for C and D. This problem works out much nicer than that, doesn't it? Because if we solve this problem, we get 0 there. This is 2 times 1, that's 2. Sine of 0 is 0, so that term is gone. C times 0 is 0, so that's gone, plus D. So from here, we get D equals -2. Now, as soon as you get D equals -2, as soon as you find that, you need to go back and rewrite your antiderivative. I'm going to rewrite it in red, show that I'm making progress. So I have 2e to the t, okay, minus 3 sine x. I'm rewriting this, plus I don't know the value of c, so I'm going to write that as cx, but I do know d is -2. Now, I have to rewrite this before I plug in my second condition. So we want to rewrite using our known constant, which in our case is D, prior to finding C. Okay. Now how am I going to find C? Well, I'm going to use the second condition. I know that I'm supposed to get 0. Remember, this is x. This is y. I'm supposed to get 0 when I plug in pi. So what is this going to be? This is going to be 2e to the pi. And what's e to the pi? E to the pi is e to the pi. Minus 3 sine pi plus c times pi minus 2. Now, unlike the previous problem, which worked out mathematically kind of simple, right? It was a simple solution, everything that comes with zeros and everybody went away. This one's going to be a little more involved. Now, sine of pi is 0, so that's nice. So this is 0. So what do we do here? We can move the 2 over. Right? We get 2 equals 2e to the pi plus c times pi. Now we can move this over here, and we get 2 minus 2e to the pi equals c times pi. And from there we can find c. C is going to be equal to 2 minus 2e to the pi divided by, and that's c. That's what c is. So our final solution, right? Our finals, we're not done. Our final solution is we have to come back here to our function, right? And we've got to rewrite it again now that we know c and now that we know d. And you're right. A better place to start with using it, right? When we've already plugged in our c. So what is our final solution? Our final solution is f of x equals 2e to the t minus 3 sine, I don't know, a little x there. I'm sure you all self-corrected that. I'm sure you all self-corrected that. And I'm sure you all self-corrected that. And I'm sure you all self-corrected that. I'm sure you all self-corrected that. Or maybe you turned the video off way back then. So we get 2e to the t minus 3 sine t, right? Plus, what's our c? Our c is 2 minus 2e to the pi all over pi times t, okay, minus 2. And this is the function whose second derivative is equal to this blue function that passes through those 2 points. All right. I hope this helps. I hope you're able to complete the homework now in section 4.8 on antiderivatives. And everybody have a wonderful day.